Next, we're going to start looking at the compound inequalities when they're connected by OR and how to solve it graphically. And in terms of process, this is actually very similar to what we did with compound inequalities connected by AND. And remember, when inequalities are connected by AND, we're looking at the part where the two intervals overlap. We're looking at the intersection. And the only difference for inequalities connected by OR, as we talked about before, is we're looking for the combination. We're looking for the part of the number line that's covered at all by at least one inequality. So to start solving this inequality by graphing, the first part is very similar. We're going to treat the two inequalities separately first and graph them individually to find the solution first and eventually combine the solution to find the final answer. And the first thing we want to do over here is to work with the two inequalities and scale everything properly on the x and y axes. And with a value I have over here, just for a simplicity reason, I'm going to scale everything to go up and down by 1 every time. And I'm going to label every other unit over here. And similarly on all directions, you can do that. And here, the first inequality we have is working with negative 2x plus 4, and we want it to be greater than or equal to negative 6. So I want to make sure these points are clear on the graph. And for the same argument, we can let y1 be equal to negative 2x plus 4 over here. And I want to connect it with the restriction negative 6 after I graph it over here. And similarly, y2 equals 1/5 x plus 6. And again, these labeling are just to make things a little bit easier to refer to for y1 and y2 and easier to label on the coordinate plane. You can use different letters or variables to represent the same thing, but because we're working with the x and y axes, I'm just going to use these labels for the linear expression over here. And now for y equals negative 2x plus 4, we can see the slope is equal to negative 2 over 1, and the y-intercept we get is 0, 4 over here. And similarly for y2, we get the slope is 1 over 5 exactly, and the y-intercept is 0, 6. So these are the information we can gather just by looking at the linear expression over here. And now if we want to go ahead and graph it, the first one we have negative 2x plus 4, meaning my starting point I'm going to use is 0, 4. And I'm going to work with restriction being negative 6. So I want to go downward direction so I can get closer to my restriction when I draw the graph. And I know the slope is negative 2. That means every time I go down by 2, I should go to the right by 1 unit. So go down by 2, go over by 1, and we can keep doing this until you think you have enough points to connect the points nicely on a linear pattern, because we have a linear equation in this case. And try to graph it again as exact as possible, because we are relying on accurate graphs in order to find the solution graphically. And in this case, that's going to be my y1 over here. And I want y1 to be bounded by negative 6. And negative 6 is included, so I'm going to use a solid line for negative 6. And even though I didn't label negative 6 as a separate line, that's implied that each side of the equation or inequality will be its own linear graph over here. So this is y equals negative 6 over here. And just as before, I'm going to go ahead and label the intersection first. So this is fairly easy to read because we're going by 1 every time. 5, negative 6 is going to be the intersection. And if I want the graph to stay above negative 6, that means I'm looking at the part of the graph that stays above the horizontal line. So I'm looking at this part of the graph. It could keep going further up or to the left in this case. And to indicate the solution from this, we can see x can be anywhere to the left of 5 because the x-coordinate is cut off at 5. So we can get x is less than or equal to 5 over here. And now for the other inequality, we're working with 1/5 x plus 6. With that information, we can get 0, 6 is our starting point. And we are looking at the slope being 1 over 5 over here. And if it helps, you might want to look at what 27 over 5 is referring to. Even if you don't use a calculator, hopefully you get the idea that we can convert 27 over 5 to be an improper or a mixed number. In this case, 5 going to 27 5 times was a remainder of 2. So this is really equal to 5 2/5 in this process. So we know it's actually exactly 5.4. So, but at least you can get the idea that's between 5 and 6 over here. That's where we're looking at. So it's below the starting point. So I'm going to go downward as well, also because I have more room downward. So if I go down by 1, that means every time I go down by 1, I should go over by 5. So that would be my next point. And similarly, if I go down by 1, I should go, I should go to the left, actually, because it's a positive slope. So we have 1, 2, 3, 4, 5. And similarly, go down by 1, I should go over by 5. 1, 2, 3, 4, 5. Right over here. And you can do one more on the further right direction. That would lead you here. And if we connect the points, we would get this line. And this is my y2 over here. And it's bounded by 5 2/5 over here. And if you haven't caught on this by now, I just want to make it clear that the solution should all have whole number solutions, just so we can get the exact value just by graphing by hand. It's a lot easier to get exact graph with technology, but without technology, we can still get the whole number solutions over here. And if we look at 5 2/5, it should be just below 5.5 over here. So it should be indicated by this line over here. And we can use a solid line over here because that restriction is inclusive over here. And if we look at it, 5 2/5 should be right over here with that intersection. And with this intersection, we get the x-coordinate is equal to -3, and the y-coordinate is 27 over 5 over here. So now if I want the y2 to stay greater than or equal to 27 over 5, I'm looking at this part of the restriction that's just above that. So I'm looking at this part, and I can keep going further and further to the right. If I want to write this out, this would look like the solution is x is greater than or equal to -3, because I'm comparing the x-coordinates. Now things are connected by or. That means I'm looking at the part that's covered by either highlighted sections of the line. And if we look at the red section, we can see it's stopped on the right by x equals 5, and it keeps going further and further to the left without bound. And similarly for the green section, it has a bound to the left, -3, and it goes all the way to the right without any bound. And imagine if you keep extending the red arrow and green arrow on negative and positive directions respectively, we can actually cover the entire number line because they're increasing or decreasing without bounds. We don't have any bound overall when we're looking at a combination of the two line segments over here. And in this case, we would actually have the result telling us that we can have all real numbers be in the solution. So we can say the solution is all real numbers if we want to use the proper notation for interval and set notation, we can say that for interval notation, this is just going to be negative infinity all the way to positive infinity. And for the set notation, you can say that it's x such that x is a real number. You can write out the sentence like this, or you can say x is just all real numbers. It's in the set of all real numbers with this fancy looking R representing this, and that will be our solution in this case. So once you think you are good with this particular problem, you can move on to number 5, and we're going to do one more example when inequalities are connected by OR. So in number 5, once you get to here, take a minute to read the questions first, and we're going to again start by scale things based on the information we have. And in this case, with the numbers we get, I'm still going to use 1 being the scale over here. So I would have 0 in this case, and I'm going to go up by 2 every time. For every 2 boxes, that's where I'm going to label things. And similarly, I can do the same thing on the negative direction. And here I have the room, so I'm just going to use the easiest scale over here to fit everything. For the same argument, I'm going to let y1 equal to 2x plus 2 and y2 equal to 2/3 x minus 2. And we can again go over the slope is 2 over 1 for the first line, and the y-intercept is 0, 2 for the first line. And then for the second line, we have the slope being 2 over 3 exactly. And the y-intercept is 0, negative 2 in this case. So let's draw one line at a time, treating one inequality at a time. So here we have 2x plus 2 to graph, meaning I'm starting from 0, 2 being the starting point, and the line has a slope of 2. So every time I go up by 2, I need to go over to the right by 1, and we can keep going over here until you have enough points. And that's going to be our line once we connect it. That's my y1. And y1 in this case is bounded by 12. So at this point, you might see the result right away even without graphing where 12 is as a result. You can see that we would actually have this part of the line highlighted when it's staying below 12 over here. But you can get the same result if you graph 12 on the coordinate plane. Here we're going to use a dotted line to indicate 12 is not included as a result. And that's y equals 12. That's a restriction. And to stay below 12, we would get the same section of the line over here. Again, it's still important for us to indicate where the intersection is over here. And as I said, all the solutions should be integer values over here. We would get 5, 12 as the intersection. So to write the solution out, we would see that x has to be less than 5 over here. Now similarly, if we were to look at the second line or second inequality altogether, we have the starting point being 0, negative 2, and we want to eventually work with a bound being 4 over here, where it's inclusive. So if you want, you could put the line y equals 4 already as the restriction. So going back to 2/3 x minus 2, we have the slope being 2 over 3. So every time I go up by 2, I need to go over by 3, go up 2, go over by 3, up 2, over by 3. We can see where it intersects with y equals 4 already over here. But here, if we were to connect all the points, we would get this is our y2 over here. And if we wanted to stay below positive 4, we are highlighting this part of the line over here. And with this information, we can see that from the green line, the highlighted part tells me it's still less than or equal to some value, and we can kind of count where things are. This would be 6, 8. So the coordinates would be 9, 4 over here. So as a result, we would say the solution for the second inequality is x is less than or equal to 9 over here. And again, they're connected by or, meaning we want to include everything that's covered at least by one line or ray over here in this case. So if we look at this, we can see if we want to include everything that's been covered at least by one part, the cutoff value is right over here. So as we keep going down, the furthest right we can go is going to be 9 for x value. And to the left, we could go further and further to negative infinity all the way. And this should be consistent to what we learned when we first introduced the compound inequality connected by or. We get the solution. We can use a set notation first. It's x such that x is going to be less than or equal to 9, because that's where the highlighted part starts to cover part of the number line for x. And we can say the set notation is over here, and the interval notation is going to be negative infinity all the way to positive 9 inclusive, because that 4 was included as part of the restriction. And that's how we solve it when it's connected by the word or.